Alright, I'm going to be using a 4x4 number cube in order to derive this algorithm. I'm going to be using old WCA notation, where lowercase letters mean inner slices and RW means wide slices. And I'm just going to show you right now what I'm aiming for so you know what's coming. It's very simple. I'm going to break this algorithm into two pieces. I'm going to break it up into R2, U2, R prime, U2, R2. And then R, U2, R prime, and U2. So this right here is what I'm aiming for, because from that point all I have to do is just, if you know parity algorithms at all, this center right here is solved, right? It's not affected by this current algorithm, but this center is. If I just would do a setup move to put this white into that white, then white is going to swap with white when I undo that setup move at the very end of the algorithm. So that's what I'm going to have. I'm going to have this, and then from this point I can write the entire algorithm on one line, merge these two as R prime and these as R prime, and then I just have the inverse of this. So that's the gist of it. So what I want to first do, I'm just going to cut this and paste this here because that's the end goal. I want to talk about this. Let's take a look at Stefan Pachmann's PLL parity algorithm. You'll recognize it if you see it. It's R2, F2, U2, R2, U2, F2, R2. Now if we take a look at this cube in the back here, maybe you can tell, maybe you can't, but just have to take my word for it if you can't, but the purple face here is solved. It's not affected by Stefan Pachmann's PLL parity algorithm. And neither is the bottom. If I turn the bottom this way, this 8 is next to this corner, that's 8, and this 7, and so forth. So the only two faces that are affected by this algorithm are the red and white. If I were to take a look at Stefan Pachmann's algorithm, this is just a conjugate of this move. So that means that all of these are setup moves, then you have one move, then they are all undone. All the setup moves are undone. If we were to therefore take a look at what the setup moves do before that half turn of the R slice, we can see what pieces are in the R slice. We have, just pay attention to this slice only, nothing else. We have two white centers and two red centers. And so therefore that's the only centers that's going to be involved with this algorithm. There's not going to be any other centers involved. And also, if we take a look at the wing edges that are in the right slice, there's two edges here that contain white stickers, and they have two in the bottom that contain white stickers. So it's only the white stickered red and purple wing edges that are going to be involved, and the red and white centers. And that's exactly how we can describe what this algorithm affects, right? If we were to finish it, that's exactly what it is, right? The red and white, purple and white wing edges, and the white center and the red center. So with that in mind, what if I were to instead do a conjugate of a quarter turn? If we were to take a look at this instead, and we do a quarter turn instead of a half turn, we would still have all the same pieces as mentioned before with the Stefan Pachmann PLL parity algorithm affected. But now what's going to happen is, if we do an R turn away from us, this center here is going to go to where this center is. This center is going to go to where this center is, and this one. So basically, the red is going to go to where the white is, and the white is going to go to where the red is. But with Stefan Pachmann's PLL parity algorithm, when you do a half turn, the white is going to go to where the white is, the red is going to go to where the red is, as we saw before. That's why we had the white that was here went to the white that's here. The red that's here went to the red that's here, and vice versa for both of them. But now, as I mentioned earlier, the white is going to go to where the red is, and the red is going to go to where the white is for both points of view. So when you do that, we're going to basically switch to adjacent centers. And now we have what's called a 4-cycle instead of what it was before, which was PLL parity, which is a 2-2 cycle. But basically, it's a quarter turn, so it's an odd permutation. That's what parity is, and that's what this algorithm is. It's an odd parity algorithm. So when there's 4, it's going to be what's called a 4-cycle. Means that this wing edge here went there, this one went there, this one went there, and this one went there. It completes a circle. And so just taking a look at this, so I'm just going to cut this and paste this down here. Maybe for later, maybe not. But just taking a look at this now, This is that same exact type of 4 cycle, right? It affected the exact same pieces as the first one, right? The wing edges, I'm saying, right? They're the exact same thing. And the same number of 1x2 center blocks. 4 of them are unsolved, but in this case, it's going to be like this instead of nice and clean like this. I mean, from this point, if we wanted to make a parity algorithm, all you would have to do is F2 and then do a center algorithm to switch these two centers. And then undo a setup move that we did at the beginning, and then you have this case. Then from this point, all you'd have to do is, you already have a 2 cycle. This is not what we want. We want to have a 4 cycle. We want to have 4 pieces unsolved. That's what this algorithm does, right? There's 4 pieces unsolved with this algorithm, and 2 1x2 center blocks that are discolored but not solved. We want to have no centers visually affected, but 4 wing edges unsolved in this fashion. But as I was just showing now, we ultimately want that to make a single edge flip algorithm, right? If we wanted to make one from this, because this center is the one unsolved, I actually have to do a setup move like this, for example, and then undo it at the end to move it on the side here, so that now I can just do a R prime, for example, and then an R to finish it off and to make a single edge flip algorithm. But that's not exactly what we want to do, but that's just showing you that it's kind of user-friendly when the unsolved centers are adjacent looking like this versus how they are like this. But this is what we have to use, as I showed earlier, to make this. But how did I get this? How does this work? All I have to do is take a look at the setup moves before the quarter turn to see what centers it involves. It involves the 2 white centers and one of the purple centers and one of the red centers, and specifically the right hand side of each of those. The left, as you can see, the left purple in the back and the left red in the front are not affected at all by the move, so it certainly will not be affected if we do quarter turn of the right slice and then undo these set of moves. This is still going to be in the same place, right? So it's clearly these centers. And the edges it affects are the same edges as PLL parity that I showed you at the beginning for Stefan Pachmann's PLL parity. That's what I mean. The same ones. And we're going to do a quarter turn, and we're going to have the same exact checkerboard-like 4 cycle that we had with this algorithm here. So if I were to just execute this algorithm, this is what we have, and that's why we have it. I could have chose to do an R instead of an R prime, and I'll show you how to deal with that in just a moment. But just to explain this part here, all this is the center algorithm. The center algorithm is basically, we want to solve back 2 1x2 centers with it. And we also want to try to keep 4 wing edges unsolved, because again, that's what we want with the goal algorithm that we want to derive. So the last thing we have to do is pay attention to how the center algorithm not just affects the centers. We already know that. We already know how to solve a cube. We already know that. But we have to pay attention to how it affects the wing edges. And an easy way to do that is actually not to use inner slice turns. It's easier to analyze the center algorithm by using outer slice turns, because when we use inner slice turns and you go up and then over and then down, you have to do that U2 and it looks really messy, right? But if I do the outer layer turns instead, and I mean wide turns, so I would do RW, U2, RW prime, and I would just ignore the left and the right slices and just only pay attention to what's on the center, then all of a sudden we see that only thing that changed is this center here switched with this one. So this one went here, this one went there. In addition, these 2 wing edges switch with each other. It looks like a 1 edge flip, right? But it's really this one went here and this one went here. And lastly, this wing edge back here went down here and this one went there. So that's all the center algorithm really does. And so if we start out with Waterman, that's the name of this algorithm, the checkerboard pattern in wide turns now, if I go R2, U2, and then R prime, and then U2 and then RW2 to finish it off, and I want to apply the center algorithm, we already know what the center algorithm does now, even before we even do it. right? It's going to switch this wing edge with this one. Is that going to solve any wing edges? No. But it's going to switch this wing edge with this wing edge. That means it's going to solve this one, but this one's going to remain unsolved. And when it switches this one with this one, it's going to unsolve the 5 and still keep the 17 unsolved. And so therefore the net result will be 4 wing edges remain unsolved, but the center here is going to switch with this one. And so that means we're going to be able to complete the white 1x2 center and the red 1x2 center. 2 centers complete out of the 4, which that means that 2 are going to be left unsolved. So the net result of combining these two together, if I were to now go RW, U2, RW prime, is in fact that result. Now, I'm very tempted to, and you have to do one more U2 to match the sides back up. That was just for visual purposes, but now to make it into single slice turns, I can just do R2, and then R, and then R prime, and then that's it. That's pretty much all we had to do, and then we just do that conjugation. Where this center here was unsolved originally, I need to put it where this one is so that white will switch with white, so that the centers are no longer discolored, and I have 4 wing edges that are unsolved at this point. And we already know at this point how this cancels to this. So let's suppose that we were to instead use the R instead of the R prime, because I said I'm going to show that towards the end. Convert these to wide turns again, and I wanted to solve back 2 1x2 centers and solve back 1 wing edge but unsolve another one. I can't just do the center algorithm starting with RW again on this side, because that would put this center here. Even though it would solve this one back, it would put this center here, right? It wouldn't be desirable. I wouldn't want this one to be here. I need to solve back 2 of the 4 centers with just 3 moves, basically, right? I can just rotate the cube around, and now I can do it, right? It's going to work from this side, because it's going to solve back the purple in this case. Of course, what it's going to do is it's going to solve back this wing edge here but unsolve this one. It's the same thing, it's just on the opposite sides, the mirror image of what we did, and we're looking at the back of the cube instead. So this is not any of the moves we've done so far. We're going to go up, turn top twice, and then move this down. That solves that center there, it solves this center, and it solves this wing edge, but it unsolved the wing edge that was there, the 23, right? It was here, as you can see, but it switched it with this one, as I mentioned before, what the center algorithm does. And that's all it does. That's it. When you have it with wide turns like this, that's all it does. It switches this center with this center, this wing edge with this wing edge, and that wing edge with that wing edge. As far as the M layer is concerned, which is what we care about. The outer layers are only affected because we're using RW turns right now for visual purposes. But we can remove those and just have this, and we know what we need to do based on the visualization we had. We just need to move this up, this over, down, and then turn this twice. And then that's it. So I can just turn this around and I can do one setup move. This case I'm going to, clearly I have to move this down to put this white center that's not affected into the slot which is affected, and then undo it at the end. Now I can merge these two, which I haven't shown before, so I'll show it now, as an R move, right? Those merge as an R move, and then these merge as an R move, and then you can just put the last move on one line, and it's the desired algorithm that we wanted to derive. Thank you very much for watching, and have a nice day.